So thank you to Penny for using your connections to get us our seminar speaker this week. Today we have Dr. Blair Trewin, who is a senior climate scientist at the Australian Bureau of Meteorology. Of course, since he received his PhD at the University of Melbourne, he has an entire career's worth of accomplishments that I can't possibly list today, but these include leading and coordinating multiple Australian and international climate reports. And he was the president of the Australian Meteorological and Oceanographic Society. Today, he will be presenting on the recent State of the Climate report, particularly discussing the top end. And we're really excited to have you here in this last minute seminar.
Okay. Thanks, and yeah, it's good to be here. It's something put together at reasonably short notice. Background to this is that one of the things I do at the Bureau is I manage the long-term temperature data set we use to assess Australian climate change, which has 112 locations in it. One of my long-term ambitions is to visit all 112 locations. I had 8 to go, and I intend to knock off 5 on this trip. So, that was a pretext for my current trip. But given I was in town, got asked to do this, so thought that this would be a good opportunity. So, State of a Climate report is oh no, that is okay. I must have taken out the background slide. So the State of the Climate report is a report that is jointly put out by the Bureau and CSIRO every 2 years. So the most recent one was issued late last year. Covers a very broad range of areas of the climate system. So covers the atmosphere, but also covers the oceans, covers the cryosphere, particularly Antarctica. Although its focus is mostly on observed climate change, there is a little bit of material in there on projected changes as well, but I'll be focusing very much on observed changes here. And this complements the the information available on a more global scale in reports such as the Intergovernmental Panel on Climate Change reports, which the most recent of which came out or in 3 parts 1 to 2 years ago. So this drills down into some more regionally specific material. So just an overview of what I'll talk about today. A lot of this talk will be looking at land climate variables, but then moving on to oceans, things like oceans, greenhouse gases, and carbon budgets, and touching on future climate as well. Okay, that's where the introduction slide was, so I'll skip over that. So starting off with the atmospheric variables, a summary of some of what we look at, and a picture which was most definitely not taken in the Northern Territory. But starting out with temperature, so Australia's temperatures warmed since national records began consistently in 1910 by a bit under 1.5 degrees, and that's fairly typical of the warming that we've seen in land areas globally. Land does warm faster than the ocean, and we see that here with the blue line showing sea surface temperature in the Australian region, and it's also warming, but not as fast as land. And both with land temperatures in the ocean, warming in the Australian region has been predominantly since the mid-20th century, which is actually a slightly different pattern to what we see globally. Globally, there was quite strong warming over the first half of the century, then levelling off from about 1945 to 75, and then renewed warming after that. A lot of that links in with greenhouse gases being offset by things like sulfur dioxide and particulates in the big northern hemisphere industrial continents, but that wasn't so much of a factor in the southern hemisphere. Now, with that increase in average temperatures, we also see an increase in national scale extreme heat events. And what this plot's looking at is days when the Australian average temperature exceeds the 99th percentile. So on average, you expect about 3.5 of these a year by definition. And we can see here that those days were pretty rare up until the 1960s, come to become a little bit more frequent over the second half of the 20th century, but really took off after 2000. And 2019 in particular was a real standout for extreme heat, both for, the 2019-20 summer is etched into the memories of a lot of people, but 2018-19 was extremely hot as well. And we also see, as well as heat waves on land, we see an increased frequency of what we call marine heat waves, with unusually warm temperatures in the ocean. And one of the most visible impacts of that in the tropical Australian region is coral bleaching, but it also has quite significant impacts on fisheries in various places. Looking at their geographic pattern, and this is just a map of trends since 1970. So on the left, we've got maximum temperatures, and on the right, minimum temperatures. And what we see of maximum temperatures is we see warming over most parts of the country, generally at its strongest in the southern interior, but everywhere is warming. You can see here that the northern tropics are warming at a somewhat slower rate than the rest of the country, and that links into some of the rainfall changes that I'll talk about a bit later on. But overnight minimum temperatures are quite interesting here in that we've seen quite strong warming in quite a lot of eastern Australia, particularly Queensland, northern New South Wales, but not much warming over this period at all in quite a bit of northwest Australia, and also relatively weak warming in southern Australia. And again, that ties into some fairly interesting changes that I'll talk about a bit more later on. So when we look at Darwin specifically, this is looking at averages at Darwin Airport, where there have been observations since 1941, although the 1940s observations were a bit erratic, basically because they had to move the observation site every time the Japanese bombed the previous one. From about 1946, the record was fairly consistent. There were also observations at the post office pre-1941, which we can make use of, but you need to be fairly careful about how you compare them. So I'll just put this up as a fairly straightforward plot, and we see with maximum temperatures for warming trend has been fairly consistent, warming by about 0.8 of a degree since the 1940s. Minimum temperatures in fairly showing what we saw on the map here, but we had reasonably solid warming from the 1940s through till about 1980, but then a levelling off since 1980, and that shows up in actually both in the core of the wet season and in the dry season, but perhaps a little bit more in the dry season. Now, one of the interesting aspects here is for frequency of temperature extremes, and what we tend to see in the tropics, because there isn't a lot of day-to-day variability in temperatures, but a relatively small shift in average temperatures can have a big impact on the number of days over extreme thresholds. And we see this pretty clearly when we look at the number of days over 35 in Darwin. Up until 2000, the average number of days per year over 35 in Darwin was about 9. But in the more recent times, in the 2000s, it was up around 20, and in the 2010s, it's averaged about 30. And in a couple of recent years, we've been over 40. So that's quite a dramatic increase in the frequency of days over 35. When we look at nights under 20. Again, linking in with the flattening out in the overall minimum temperature trend. We see there's a period in the 1980s and 90s when nights below 20, which of course are almost exclusively in the dry season, were relatively uncommon. But since the 1990s, they've rebounded to levels which were typical of the 1970s and earlier. You can see there's a lot of year-to-year variability there, which probably doesn't surprise anybody who lives here. This actually links in quite well with changes in atmospheric moisture. So this is looking at the dew point as a measure of humidity. And in the wet season, we see a slight increase, more or less in line with the increase in temperatures. And there's very little year-to-year variability. But in the dry season, we've seen a decline in dew point. Now, and particularly since the 1990s. Now, a few bits of the puzzle which need to be put together here, but that's indicative of an increase in the occurrence of southeasterly surges during the dry season, which we've experienced a very nice example in the last couple of weeks. We've established that those tend to be particularly frequent in years when there's unusually strong high pressure over southern Australia, which in turn links into the drying we see in winter in southern Australia. There hasn't yet been research work done on linking together all the bits in the chain, but it seems at least plausible that there's a reasonable connection between that strengthening of the subtropical high and the increased frequency of subtropical surges into here. And what that illustrates is that even though the overall climate globally is warming, at a local scale you can get local weather type effects that can offset that warming, or in other cases amplify it. Another quite interesting one here is looking at days with maximum temperatures below 30 in Darwin. I forgot to put the labels on this one, but the orange one is for dry season and the blue one is for wet season. So what we see here is that the number of days below 30 in the wet season has basically not changed. It's averaged about 15 a year, pretty well right through from the 1940s to the present. And when you think about what gives you a day below 30 in the wet season, it's a day when it rains, when it rains a fair bit of the day, basically. But in the dry season, where the likelihood of a day under 30 is a function of how warm the fundamental underlying air mass is, we see a very strong drop off from around 40 days a year in the 1950s. So getting close to 50% of the days in the June to August period, whereas in the modern era it's struggling to average 10 a year, and 2020 I think only had 2. We did have quite a number last year, of course. We had a quite cool spell in the middle of the year, but that's become the exception rather than the rule. Moving away from temperature now and looking at fire weather, which is an area of interest in many parts of Australia, and we do have an increase in the frequency of dangerous fire weather days across many parts of Australia. Now, of course, fire weather is not the only element in fire risk, particularly in the more arid parts of Australia. Fuel availability is a major driver as well, and certainly on the evidence I've seen in my travelling, fuel availability is very abundant in a lot of areas, with a very big wet season we've had. But we see particularly strong increases in the frequency of dangerous fire weather days in a lot of eastern Australia, and that shows up particularly as a lengthening in the fire season. Whereas in southeastern Australia, spring was often a fairly quiet period for fires. The season is increasingly coming forward into spring there, which creates quite some complications for fire management in that part of the world, partly because it means you've got a much shorter season to do burning off, given that in southern Australia burning off is usually not practical during winter. But also, an element people probably don't think of is we share a lot of firefighting resources with the North Americans, and the North, at the same time as our season's coming forward into spring, theirs is getting later and later into autumn. So you're increasingly getting periods that are active fire season in both hemispheres, so it makes things a lot harder. Now moving on to rainfall, and one of the standout things we see for rainfall at the national scale is that there's been a drop-off in rainfall in a lot of southern Australia during the cooler months, which is when a lot of the, particularly the agriculturally important rainfall and the rainfall important for water supply happens. Southwest and Western Australia was the first to experience this. They've had a downward trend in rainfall since the 1970s, and then more recently from the 1990s in the southeast. Both of those regions have had very protracted droughts in recent decades, and for relatively wet conditions we saw last year, only really a blip in that context. But when we look at the northern wet season, it's a completely different story. So we see high rainfall across many parts of northern and central Australia. Perhaps not quite so much so, relatively speaking, in the top end as in the Kimberley and further south in the Northern Territory, but still definitely an increase in many parts of tropical Australia. And drilling down into this a little bit more, this is looking at Darwin, where we do have rainfall records going right back to 1870. And what we see here is there's a fairly pronounced jump in rainfall around the 1960s. Pre-1960s, averaging fairly consistently around 1,500 millimetres a year, and then after 1970, it's been closer to 1,800. And there's been a much higher frequency of very wet years. We've had a number of years since the 1970s over 2,500, which were entirely absent in that pre-1970 period. Dry years have also become less frequent, although in years like 2019 show that they can still happen, but they have become somewhat less frequent. If we look a little bit further south in the Territory, we don't have a lot of really long-term rainfall stations in the Northern Territory, but Victoria River Downs is one, southwest of Katherine. And here we see a broadly similar pattern to Darwin, but changes are relatively bigger. So instead of going from 1,500 to 1,800, they've gone from 600 to 800, which is a somewhat bigger percentage change. Although the severity of the 2019 drought really stands out here as well. I suspect the 2023 numbers are going to look quite impressive when it goes on here. Now, average rainfall is one thing, but heavy rainfall is an area of particular interest, particularly with so obviously it's a big driver at flood risk, and it's fairly well established that we, in a warmer world, we would expect more heavy rainfall. The fundamental driver there is that all other things being equal, air that is 1 degree warmer can hold about 7% more moisture. Of course, all other things are not necessarily equal, and but we see, looking at observed heavy rainfall in Australia, that at sub-daily timescales, so our intense rainfall on timescales of say an hour, we do see a clear increase. But when we look at daily and multi-day rainfall, it's a bit more inconsistent. We see increases in a lot of northern Australia, but many other parts of the country there's no clear trend. Part of the background to that is that the natural variability in Australian rainfall is unusually high by global standards, and in particular, we tend to get more very heavy rainfall events than other parts of the world with similar amounts of average rainfall. And because of that high variability, it's quite a bit harder to separate any climate change signal from the variability. So what we see, and this is just reported in IPCC, is that whereas most of the major northern hemisphere continents do show a clear observed increase in the frequency of extreme daily rainfall, in most of Australia the observed trend is not yet clear. That doesn't mean there isn't one. It just means that any trend that may be there is not yet big enough to have emerged from the natural variability. Now, when you're looking at flooding, of course, rainfall is a very big driver, but you also need to look at what changes in land use there might have been, in catchments that have dams. That obviously has an influence as well. So it gets quite complicated. And when we look at heavy rainfall days at Darwin, I've just taken 50 millimetres as fairly arbitrary threshold here, and we see it's tracked. Its changes are tracked fairly closely with the changes in average rainfall, but we see basically no trend through till the 1950s, and then something of a jump from the 1960s onwards. We do see a decrease in stream flow at the majority of sites over the period from the 1970s to the present, which is quite interesting. We see a decrease in stream flow in some of the top end streams, even with the increase in rainfall, although it must be said that the stream flow data set starts in the 1970s, so the long-term rainfall increase had largely already happened by then. We do see more clear-cut increases in the Kimberley. Much of Eastern Australia and Southwestern Australia does show fairly consistent decreases in stream flow. Now, an area of particular interest, of course, in this part of the world is tropical cyclones, and the number of tropical cyclones is actually declining in the Australian region since we started getting satellite data on tropical cyclones from about 1970 and fairly consistent satellite data from about 1982 onwards. Before then, we know that some cyclones were likely missed because, particularly ones over the open ocean, unless a ship was unlucky enough to run into one and lucky enough to live to tell the tale, we didn't get to find out about it. But for the relatively heavily populated Queensland coast, we have good enough data back to 1900 to know that the trend in cyclone number decline has occurred there as well. Now, the expectation is with climate change that we would see fewer tropical cyclones, but the proportion of those cyclones which are intense would increase. At global scale, we do see reasonable evidence of that. At national scale, again, because it's a fairly small sample, we don't yet have a clear signal for that in the Australian region. Perhaps the most clear-cut signal we see with tropical cyclones, although again, the evidence is clearer at the global scale than at the Australian national scale, is that the amount of rainfall that a tropical cyclone of given intensity is capable of increasing shows a fairly clear increase. And of course, we've seen a couple of cyclones in this last season, which never got above category 1 or 2, but ended up being massive rain producers. So perhaps illustrative of that. One of probably not much interest to the territory, but interest more generally is that, as you would expect with warming temperatures, we see a decrease in the amount of snowfall in the higher parts of Australia. That's happening most prominently early and late in the season at lower elevations. Higher elevations in the core of the season, snow cover is holding up better for now, but with further warming, that may not be the case. The seasonal peaks also tending to occur a little bit earlier than it previously did. Now, Antarctic sea ice is quite an interesting one. That whereas the Arctic, which is the orange plot here, has shown a pretty clear and consistent decrease in sea ice extent since satellite records began, the Antarctic actually was showing an increase until the mid-2010s, and then fell through the floor. And in fact, since this plot was produced last year, it's fallen even further and is now tracking lowest on record for the time of year by quite a significant margin. Noting here that the two environments are quite different. So, the Arctic is a polar ocean, and much of the ice there, although less than used to be the case, is relatively long-lived. Whereas the Antarctic sea ice, about 90% of it melts and refreezes every year. So, there's not so much long-term ice there. But I think up until about the mid-2010s, the increase in Antarctic sea ice was one of the areas which we weren't quite sure about what was going on, and as it turned out, that change didn't last. So moving on to the oceans now, and looking first at sea surface temperature, and we see warming of sea surface temperatures around Australia, a little bit less so in northern Australian waters than in some other parts of the country, but even in northern Australian waters, we're seeing warming of close to 0.1 of a degree per decade, and you tend to get less year-to-year variability in sea surface temperature in the Australian region than you do with land temperature. So the trends seem to be a bit more clear cut. When we go below the surface, if we look at the overall ocean heat content, down to the 2,000 metre depth level, world's oceans take up 91% of the extra energy generated as a result of enhanced greenhouse gas concentration. So the oceans are a really, really important part of the climate system. And we can see here that the ocean heat content has just been going up and up with very little year-to-year variability. Whereas global surface temperature has quite a bit of variability from year to year, driven particularly by El Nino and La Nina. In the deep oceans, that's largely absent, and we see a much more consistent trend here. Now, with sea level, global mean sea level is rising, and that rate of rise is increasing. It's again, the most reliable readings are since satellite records began, which for sea levels 1993, and is about 3.5 to 4 millimetres a year. When we look at the overall patterns around Australia, the contours, satellite, and the dots are tide gauges where they exist. One thing which is quite interesting here is the apparently very strong sea level rise in the Gulf of Carpentaria, but that's actually largely an artefact of El Nino and La Nina and the time period chosen, because the sea levels in the Gulf respond really strongly to El Nino and La Nina. They can, in an El Nino year, they can be 15 or 20 centimetres lower than average, in La Nina 15 or 20 centimetres higher. And some of you may remember the big mangrove dieback in the Gulf in the 2015-16 El Nino, and it's largely driven by unusually low sea level combined with high temperatures. And because the satellite record, the first few years of it had a big cluster of El Ninos, the trend showing here is probably a bit exaggerated, but we do see rising sea level trends around the whole Australian coastline, and with that comes an increase in the risk of coastal inundation in vulnerable areas, increase in the risk of damage to storm surges in vulnerable areas. In this part of the world, obviously you've got the massive tide ranges, so that to some extent the sea level rise signal is lost a bit in the tide, in the tidal noise, but still definitely worth keeping an eye on. And areas such as the Torres Strait Islands, of course, are massively vulnerable. Now, of course, the big driver for all of this is increase in the concentration of greenhouse gases, and we have one of the main long-term greenhouse gas monitoring stations globally at Cape Grim in northwest Tasmania. The big advantage of that as a location is that under normal circumstances, the air coming towards it is coming over thousands and thousands of kilometres of ocean. So, it's sampling the broader atmosphere. It's not sampling local pollution sources. One of the other major monitoring sites is Mauna Loa in Hawaii, which is also relatively remote from major pollution sources, but is also about 3,500 metres elevation, so above surface layer stuff. But what we see is that carbon dioxide levels are increasing consistently. The rate is accelerating slightly over decades. If we look at older records and indirect records through ice cores, which are really useful for carbon dioxide, we get a very clear picture of a rise from around 280 parts per million in the pre-industrial period to the 410s where we are now. Now, carbon dioxide is not the only greenhouse gas. Methane and nitrous oxide are also significant, and then there are a number of other trace gases. So we sometimes speak in terms of CO2 equivalent, which is the signal coming from CO2 plus all the trace gases. and that's also rising at a fairly similar rate. And when you look at the individual gases, this comes clearer. This shows it in a much longer term perspective. So we can see here the pre-industrial baseline levels derived from ice cores and the extent of the increase that we've seen during the industrial period. When we look at what the actual global carbon budget here, what we see here is that globally emissions are about 40 gigatons per year. Much of that comes from fossil fuel use. At a global scale, land use change is still a net source of CO2. In Australia, it's actually a net sink now, whereas historically it had been a source. But globally, it's still a net source. Now, of that 40 gigatons, about 10% of that goes into the ocean. About 10% of it is taken up by what's called the land sink, so vegetation essentially, and the rest remains in the atmosphere and drives further warming. So, although the land and the ocean absorb some of the CO2, quite a bit of it remains in the atmosphere. You'll notice just right at the very end of that graph that there are indications that global emissions are starting to level off. Obviously, you had a downward blip during COVID, but even pre-2020, there were signs that things were starting to level off. But leveling off is not going to be enough to avert future climate change. And that is the last part here. But what this is showing is that the blue and black lines are showing what has actually happened globally. And in Australia, it's actually Australia. Sorry, Australia. The shaded blue, what that's showing is what the climate models simulate we would have expected to have happened over the last 110 years, given what we know about the changes that have already happened in greenhouse gases and other human influences like aerosols and also natural factors such as volcanic eruptions and solar changes. And you can see that fits pretty well with the actual observations. The orange shade shows a projected range of potential changes over the next 20 or so years. Now, because there's about a 20-year lag between a change in emissions pathway and resultant changes in temperatures, because that's how long it takes for climate systems to get back into equilibrium. The projected changes over the next 20 years are largely independent of what happens to emissions. Changes we'll see over the next 20 years are largely determined by the emissions that have already happened. What happens from here will determine what happens beyond that 2040 mark, and whether we see stabilisation or further warming beyond that. With that overall warming, we see you still get the occasional relatively mild year, but you see an increasing frequency of very warm years and an increasing frequency of record-breaking years. And we see that even more at global scale, where the year-to-year variability is less. So you probably saw the news reports last week about it being reported that there's a 98% chance of global record high temperature being broken in the next 5 years. What that's reflecting actually is that the last three, because global temperatures tend to be about 0.1 of a degree cooler during La Nina years and other years, the La Nina years we've had for the last 3 years have held global temperatures back, and if you like, the real underlying temperatures are probably 0.1 or so of a degree higher than what we've actually seen in the last 3 years. And even with that, we've been getting quite close to records in the last 3 years. So once you take that influence out, it's and with that, with that temperature change, we're expecting to see a large number of other changes. So, expecting to see many of the changes that I've talked about here continue. One interesting one, though, is that it's not clear cut, but the increased rainfall in Northern Australia will continue. It's most models show no clear signal towards either an upward or downward trend in Northern Australia, whereas they are much more confident on the cool season rainfall decline in the south continuing. So that's a significant area of uncertainty for this part of the world. So that gives a quick overview of the report. The report itself is on the Bureau and CSIRO website, so you can drill down quite a bit more detail there. But hopefully it's been a worthwhile presentation. I guess we open it up for questions.
Do you have questions? Thank you so much.
I realise it's probably extending past the data that you've got for Australia, but I hear quite a lot about long-term change or climate cycles and an 80-year cycle, something that I've heard a lot of reference to, and also suggestions that we're heading into a cooler period. Doesn't seem to accord with what you've just been showing us today. Have you got any comment on those, that longer-term cycle?
Yeah, well, the most prominent cycle, if you like, of that type is the solar cycle, which is roughly an 11-year cycle of slightly higher or lower incoming solar radiation. But the impact of that on global temperatures is tiny compared to the impact of greenhouse gases. The solar impact is probably in the order of a few hundredths of a degree rather than a few tenths.
Mm-hmm.
And then, of course, you've got much longer term stuff on timescales of many thousands of years that have in the past driven ice ages. But you're talking on much longer timescales than what we're dealing with here.
Yeah. Okay. So I guess from what you're indicating there is obviously an 11-year cycle. You're not suggesting there's much evidence of a sort of an intermediate, or the 80 type. Yeah. No, not. Okay. Thank you.
I just had a question about you saying the prediction is actually for less cyclones. What's the reason for that?
Well, fewer cyclones, but more intense. More intense part is driven largely by increased sea surface temperatures, but decreased cyclone formation driven largely by changes in the upper atmosphere winds, making it harder for cyclones to get started.
Like a shear?
Yeah.
Yeah, thanks for that. So once the world gets to net zero emissions, whenever that might be, what then happens to the concentration of greenhouse gases in the atmosphere? Does it just stay that way for a long time, or they dissipate, or what happens?
Great. You would, if the world does manage to get to net zero emissions, which is a very significant if, obviously, but you would start to see a slow decline in greenhouse gas concentrations as they get taken up by the land and ocean sinks. That would actually show up most quickly in methane, because methane's residence time in the atmosphere is quite a bit shorter than carbon dioxide's. But what we see in climate projections is that essentially, in fairly rough terms, stabilisation of climate at any level requires reaching net zero emissions, and the level at which that stabilisation occurs is essentially a function of the total quantity of emissions between now and whenever net zero occurs.
Can you give us an indication of the rates at which either carbon dioxide or methane start to decline in the absence of new emissions?
Yeah, not off the top of my head. It'd be slow relative to the increase that we've seen over the last 50 years.
Yeah, are you able to comment on what you think about our chances of the models better predicting rainfall for Northern Australia in the future?
Yeah. Yeah, well, as I said, there's no clear signal one way or the other, and there's actually quite a large spread between models, which indicates that models are struggling to capture the all of the processes involved in driving the observed changes in rainfall. The thing with climate models is that they're although they're getting better, they're still at quite broad scale. Generally tens of kilometres, and a lot of tropical rainfall is driven by systems on smaller length scales than that. So quite hard to capture everything in models.
Yeah. Is it, are we starting to get sort of the understanding of, for example, what's driven that increase?
There's been various bits of work done which have suggested that in part there may have been if you like, a destabilisation of the monsoon driven partly by the industrial pollution in the northern hemisphere, but I think that's still a relatively low confidence finding, but that's one possible mechanism that's been put forward. Yeah. Okay. Okay. That one's. I think that one I've already dealt with. So presumably the question, Darwin benefits from breezes to provide her thermal comfort. I assume that's referring to sea breezes. With a warming climate and sea temperatures, are you able to provide any comment on regular day-to-day wind speeds? Now, one would expect that with land generally warming faster than ocean, that you might expect to see a strengthening in sea breeze circulations, but it's at a fairly micro scale, and I don't think much work has been done on that, but that would at least seem a plausible mechanism to me. And I've noted actually in some of my own work looking at observed temperature changes, but in some of the east coastal cities like Sydney and Brisbane, that there's stronger warming in the inland suburbs than there is on the coast.
Any other questions?
You said there was a lag in the temperature response to changes in CO2, etc. The time that you've estimated there is 20 years. Is there much certainty on that? Does it change from place to place?
This is at the global scale. Of course, you'll have all sorts of local variability imposed on that, but that's talking at the global scale. Yeah.
I just had a comment, not about your talk, Blair.
Yeah.
Thank you. It's absolutely wonderful. And I'm not closing the conversation, but just wanted to thank Suzanne Casanova from Territory NRM for bumping into me at the shops on Saturday, telling me that you were here and that she thought Real would be a good place for you to speak. So I think we've got some Territory NRM colleagues in the audience maybe. So just wanted to mention that. Thanks.
Yeah, Blair, the 20-year lag in the temperature, global temperature, does that mean we've sort of locked in that 2-degree temperature rise?
Not two. It's hard to see how we don't get to around 1.5, 1.6, and in fact more, if you like, the more optimistic scenarios, for relatively rapid net zero scenarios, which have us leveling out about 1.5. Most of them involve a small level of overshoot and then gradually easing back to 1.5. But it's very unlikely we'll be able to stay below 1.5, but we might be able to come back to it after overshooting it. 2 degrees. would staying under 2 degrees would require a reasonably rapid transition to net zero. But I think I saw somewhere the other day that with all of the national net zero pledges that have been made actually get delivered, that we would have a reasonably high probability of staying under 2 degrees.
Thanks, Blair. I enjoyed it. Sorry, everybody, for putting you through all the statistics and the numbers, but I'm just fascinated by it. And I've emailed out some things that Blair's sent me over the years, and I was like, okay, fine, let's just have a presentation. But so this is Australia's State of the Climate report. How does it compare to what other countries put out?
Look, every country does its own level of reporting, and of course we're in the unique position that we're a country that's also a continent. So in some ways that makes it a relatively clean story to tell. But certainly other countries of comparable size, like the US, have similar material in some form or other. In Europe, some countries have more than others, but as you might expect, the capacity to do national scale climate change assessments varies quite a bit from country to country, although there are some countries with fairly limited resources often struggle in this space, which is one of the things the IPCC really had to focus on this time round, on providing tools to help countries that have limited capacity of their own to be able to make climate change assessments.
We can continue this conversation in our time.
Okay, thanks. Yeah, thanks. Good to be here.
It's on, it's off, never know.
Okay.
No, you three